Welcome to this lecture on the fundamentals of biomolecules. Today, we are going to dive into the fascinating world of lipids. We will explore their unique chemical structures, how they are classified, and the absolutely vital roles they play in living organisms. By the end of this session, you will understand why life as we know it simply could not exist without these incredible molecules. To understand what lipids are, think of building a house and managing a household budget. Carbohydrates are like the quick cash in your wallet, easily spent but hard to store in large amounts. Lipids, on the other hand, are like the gold bars locked in a safe for long-term, high-density energy storage. Furthermore, lipids act as the waterproof bricks that make up the walls of the house, which represent our cell membranes. Without these waterproof bricks, the house would dissolve in the rain, which is exactly why oil and water do not mix. They are nature's ultimate waterproofing molecules. They are nature's ultimate protection molecules. Now that we understand their purpose, let us look at their chemical nature. Lipids are a diverse group of organic compounds that share one major physical property. They are insoluble in water, but highly soluble in nonpolar solvents like ether or chloroform. Unlike proteins or carbohydrates, lipids are not true polymers made of repeating monomer units. Instead, they are complex molecules built primarily from long hydrocarbon chains or fused carbon rings. This unique structure gives them a dual nature called amphipathicity, allowing them to spontaneously form complex structures like cellular membranes in an aqueous environment. Building on their chemical properties, let us see how lipids are classified. They are broadly divided into three categories. Simple lipids, like triacylglycerols, serve as the most efficient form of stored energy in the body. Complex lipids, such as phospholipids and glycolipids, are the fundamental architects of the cell membrane, creating a highly selective barrier. Finally, derived lipids, like steroids, such as cholesterol, maintain membrane fluidity and act as essential precursors for vital hormones like testosterone and estrogen. Without these diverse lipids, our nerves would lack insulation, and our cells would literally burst open. Let us zoom in on the core building blocks for many of these lipids, the fatty acids. A saturated fatty acid can be represented by a general chemical formula. One end is the methyl group, also known as the omega end, which forms the start of a long, water-fearing hydrocarbon tail. The other end is the carboxylic acid group, which is water-loving and interacts with the aqueous environment. As the number of carbon atoms in the central chain increases, the melting point of the fatty acid also increases because longer chains form stronger van der Waals interactions with neighboring molecules. Knowing the basic structure, we must now learn how scientists name these molecules. Biologists use a standard nomenclature system to describe the exact structure of a fatty acid. In a designation like 18:2 delta 912, the first number tells us the total number of carbon atoms in the chain. The second number tells us how many double bonds are present. The numbers in the superscript of the delta symbol indicate the exact positions of these double bonds, counting from the carboxyl carbon as carbon number 1. This system gives us a complete structural map. This nomenclature leads us to an important nutritional classification using a simple formula. The omega value tells us where the first double bond appears when counting from the methyl end rather than the carboxyl end. In this formula, omega represents that target position. C stands for the total number of carbon atoms in the entire fatty acid chain. Delta represents the position of the highest numbered double bond when counting from the carboxyl end. If the total chain length increases while the double bond position remains the same, the omega value will physically increase, changing the nutritional category of the fat. Let us apply this formula to a concrete example. A biology student is analyzing a lipid sample, denoted as 18:2 delta 9:12. We need to classify it into its proper nutritional omega family. First, we identify what is given. The total carbon count is exactly 18 atoms. The highest delta position, which is the double bond closest to the methyl end, is 12. We substitute these values into our formula, subtracting 12 from 18. The result is 6. This means the first double bond occurs at carbon 6 from the methyl end, making this an essential omega-6 fatty acid. Now that we have classified lipids, let us examine their most famous role: energy storage. A typical carbohydrate yields an energy density of about 4 kilocalories per gram. However, a lipid in the form of a triacylglycerol yields an energy density of about 9 kilocalories per gram. This means lipids provide more than double the energy per gram compared to carbohydrates or proteins. This incredible energy density is absolutely crucial for mobile organisms, like migrating birds, because it allows them to carry massive energy reserves without being weighed down by excess body mass. To quantify this energy advantage, we use a straightforward energy equation. Conceptually, the total energy is just the amount of material you have multiplied by how much energy each unit of that material holds. In this formula, E represents the total stored energy, measured in kilocalories. The variable m represents the mass of the storage molecule, measured in grams. The symbol ρ represents the energy density of the specific molecule, which is a constant 9 kilocalories per gram for lipids. If the mass of the stored fat increases, the total available energy will increase in a direct linear proportion. Let us see this formula in action with a real-world scenario. Consider a migrating bird that has stored exactly 50 grams of fat in its body for a long journey. We need to calculate the total amount of energy stored in this fat reserve. We choose our energy formula because it directly relates mass to total calories. We substitute the given mass of 50 grams and the lipid energy density of 9 kilocalories per gram. Multiplying these together yields 450. This means the bird has an absolute reserve of 450 kilocalories locked away to fuel its flight. Having found the total energy, we can now mathematically prove why the bird stores fat instead of carbohydrates. This chunk of our proof sets up the comparison. We want to find out how heavy the bird would be if it stored this exact same 450 kilocalories using carbohydrates. We know the carbohydrate energy density is only 4 kilocalories per gram. To find the required mass, we take our original energy equation and rearrange it algebraically, dividing the total energy, E, by the carbohydrate energy density, ρ. This sets us up perfectly for the final calculation. Continuing our derivation, we now substitute our specific numbers into the rearranged formula. We divide the total energy of 450 kilocalories by the carbohydrate density of 4 kilocalories per gram. The mathematical result is 112.5 grams. The intuition here is striking. To get the exact same energy payoff, the bird would need to carry more than double the weight in carbohydrates compared to the 50 grams of fat. This mathematical proof perfectly illustrates why lipids are the superior biological choice for long-term energy storage in mobile organisms. Beyond energy storage, lipids physically build our cells, as we can see in this diagram. You are looking at a cross-section of a phospholipid bilayer, the foundation of all cell membranes. Notice the blue circular structures on the top and bottom edges? These are the hydrophilic, water-loving heads interacting directly with the aqueous environment inside and outside the cell. Pointing inward, away from the water, are the yellow wavy lines, representing the hydrophobic hydrocarbon tails. This diagram beautifully teaches how the amphipathic nature of lipids allows them to spontaneously self-assemble into a protective, highly selective barrier for the cell. We have covered a tremendous amount of ground today, so let us reinforce the most important ideas. First, lipids are unique, water-insoluble, amphipathic molecules that are absolutely essential for biological life. Second, because of their high ratio of carbon-hydrogen bonds, they provide the most efficient, energy-dense storage system in biology, far surpassing carbohydrates. Finally, their unique structure allows them to spontaneously form the protective boundaries of all living cells. You now have a solid understanding of how lipids maintain physical integrity and manage long-term energy resources. Great job completing this fundamental topic.